Hi, in this video we are going to see about in-car computers in domestic and consumer appliances. Outline: every minute of the day someone somewhere dies in a road accident because a driver had made a human but fatal mistake. With more traffic on the roads today than ever before, many traffic engineers long for the day when each car will be controlled by a computer and the driver can sit back in his seat knowing that the computer will steer him safely clear of all potential accidents and traffic jams. Much of the basic technology for this kind of control already exists, but for the foreseeable future, at least silicon chip microprocessors will be used to monitor and control just a few specific functions on a conventionally driven car. Applications: extent use of integrated circuits will result in electronics taking over more complex jobs in the car's command and control systems. Solid state devices contain no inherent wear out mechanisms. Because of their proven reliability, solid state devices and systems are perhaps the only practical and economical way to realize safety, environmental cleanliness, and the convenience required for the state of the art automobiles. Considerable progress has already been made toward reducing pollution from automobiles. This table shows possible applications of solid state devices in automobiles. This figure shows various items being offered by Ford, though not all of them are available on all Ford cars. The system shows are all electronic. This figure shows how a computer might control a car. Sensors 3 are located throughout the car to monitor such things as oil pressure, engine temperature, and the amount of fuel. A greater difficulty is avoiding the setting up of unwanted oscillations. This is because the control system forms a closed loop. The brakes sense a signal to the computer. The computer sends a signal back to the brakes telling them to ease off brake or brake harder. If the system is designed and adjusted correctly, then the difference between what the brakes are doing and what the computer wants them to do will get progressively smaller as the information and command signals messages continue. But in some cases, the computer might overcorrect the error. The result is that the error will get progressively larger instead of smaller and the system will go into oscillation. It is clear that the problem of interfacing are far more of an obstacle to the development of the computerized car than the computer itself. Electronic ignition. Development of electronic fuel supply and ignition controls has been given an extra boost by the introduction of strict laws governing the amount of pollution gases that may be present in the exhaust. Many cars now have electronic ignition. Although most are still timed mechanically, a number of more recent systems has begun to incorporate microprocessor to improve the accuracy with which the ignition is timed to fire the spark plug. Data is supplied to the microprocessor concerning engine speed, the position of the piston, and the load on the engine. The microprocessor then compares the information it receives with instructions imprinted in its memory during manufacture. This sort of facility had already been shown to improve performance and reduce toxic emissions. Electronic operation of the engine valves open up a further enormous range of possibilities. It would, for instance, allow the driver to change the characteristics of his engine at will. At the flick of a switch, he could change the car from a highly tuned Sportster to an economical sludger with plenty of pulling power simply by altering the time and duration of valve opening. Electronic ignition lock system. In the electronic ignition lock system, to prevent drunken driving, the basic idea is to flash an arbitrary sequence of letters on a screen very briefly and then require the driver to punch a set of buttons in the same order. Tests have shown that better discrimination between drivers who are drunk and those who simply have poor retention of visual images is obtained by requiring the task to performed in several short sequences rather one long sequence. This shows the example. This block diagram shows the electronic ignition lock system. In this, the sequence detector checks the sequence. If an error is made in any sequence, the error signal E is used to disable the system. If a sequence is correctly completed, a pulse is issued on one of the lines P1, P2 or P3 corresponding to sequence 1, 2 or 3 respectively. The information is compared by the comparator with the number of the sequences that was displayed. If they agree for sequence 1 or 2, the counter is stepped to the next number to start the next sequence. After agreement on sequence 3, the ignition is turned on. If the pulse received by the comparator does not match the contents of the counter, a disabling error signal is issued by the comparator. The keypad is used so constructed that each button may be pushed only once for a given sequence. A1 level will be supplied to the comparator by the keyboard on a line labeled completely after the fourth button has been depressed. The comparator will ignore any pulse inputs occurring before complete equal to 1. Anti-lock braking system. The ABS is an advanced braking system which comes into play when there is a panic brake situation. The braking action with and without ABS is shown in the following figure. In Gazelle, when a part of the car without ABS is on a slippery surface and the brake is applied, the car swirls. The car with ABS stays on course. In case 2, while taking a curve, the car without ABS goes off course while the one with ABS stays on course. In this case, when brakes are applied in a panic situation, the rear wheels get locked and the vehicle skids. This effectively increases the braking distance. ABS reduces the skid effect and helps the vehicle to stay on course. The system takes over the braking action only during sudden braking. The figure shows the ABS and without ABS. Electronically controlled suspension. This system has been designed to keep the car flat and level when riding over bumps, braking, accelerator and concerning. Figure shows the active electronic control suspension. The processor has sensors which detect steering angle, gravity, road speed, the height of the vehicle at the front and rear, the accelerator position and the rate of the movement of various suspension components. When considering, for example, 2 sets of sensors are used. Either the steering angle and vehicle speed inputs determine the processor instruction to the air springs and damper value, or a triaxial G-force accelerometer informs the processor of latent acceleration so that changes can be made. One of the most uncomfortable side effects of a soft riding suspension system is pitch and bounce. The car either bounces vertically over sympathy bumps or pitches back and forth over bumps which are asynchronous with the car's suspension. By monitoring front-rear suspension heights relationships and suspension travel, the processor can instruct the offending wheel's dampers values to change characteristics and eliminate the unwanted movement. Instrument panel display. Instrument panel displays in the form of instrument clusters act as information source for the driver. Instrument clusters usually display parameters like speed, RPM, fuel level, coolant temperature, distance traveled, trip meter and various alarms as individual displays. Trip computers used in present day cars are incorporated as separate units or are integrated as part of the vehicle instrument clusters on the dashboard. Figure shows the dashboard computer for motor vehicle. Ultrasonic car safety belt system. One of the results of car safety belt system developed by Ford mean that even the car thief will have to strap himself in if he wishes to make off with his booty. The belt must not only be fastened but also positioned correctly across the wear. Figure shows the block diagram of the car safety belt system. Airbag system. The system prevents the driver and front seat passenger from crashing against the steering wheel and into the windshield. Figure shows the block diagram of airbag system. Vehicle proximity detection system. Over 500,000 automobile accidents each year results from improper overtaking. This frightened statistic might be reduced substantially if a near solid state detection system developed. Figure shows the detection system block diagram. Navigation system block diagram. Thank you.